Okay, good morning all. First of all, let me know, is audio and video both are clear for you guys? Is both audio and video clear? So you can reply with a message. Okay, so today we start a new topic, the last part of this basic mathematics, that is vectors. So already in your schooling you come across a term, this vectors and the scalars. So first of all, let me hear from you guys, like what do you understand by scalar or what do you understand by vector? Okay, what is a vector or what is a scalar, or why we are supposed to discuss regarding this vector? Yeah, you can comment in the chat box, guys, why we need to learn regarding this vectors, how it is going to help in physics. Okay, how, I mean, where we use this in physics. So basically, before going for the history of the vectors, we need to discuss a small story, guys. Here, a small story told by this one of the scientists, Feynman. So what he said is, basically whatever we see in the nature, okay, everything that present in the nature and the behavior of everything present in the nature, he compared with this with a game. Maybe in the class 1 I discussed that already. So everything present in the nature, Feynman, the scientist Feynman, compared that thing with a chess game. So the space he compared with the chessboard, and everything that we see or we feel in the nature, he compared with yeah, am I not audible to you guys? Is this audible now? Let me know, is my voice audible? Yeah. So let's get back to our story. It says that the scientist says the space, I mean, the compare the space with a chessboard, and everything that we see in nature and that we feel, that we can measure, whatever the quantity that we take, I mean how much quantity, how much amount of that thing is there, that's what the quantity or whatever we see in the nature, that he compared with the chess coins. Alright, still the voice is not audible, guys. Let me know, is the voice audible now? Is my voice audible? Am I audible to you guys? Okay, so that's what the Feynman compared everything that we see in the nature with the chess coin and the space with the chessboard. Why? Because in the chessboard, whenever I want to move a coin, randomly I cannot move it, right? Depending on which coin it is, it follows different paths following the given rules and regulations, whatever we talk about that, how a coin can move. Alright, the king can take only single step in all possible directions wherever there is empty gap. Okay, and next, coming to the let's say, if at all I consider a knight, okay, you call it as horse, basically that takes L shape in all possible ways, okay, wherever there is an empty gap. Likewise, different coins in a chess game moves in different styles, I mean to say that different rules and regulations. Okay. Same way, in the space that we compared with a chessboard, we have many things in the nature. Alright. Likewise, if I consider maybe a length, mass, time, momentum, velocity, acceleration, likewise many things were present in the nature. Now what we observe from the observations, it is seen that each and everything, just like a rule and regulation in the chess game, how a coin moves, the similar way, each and everything is this audible, guys? So similarly, each and everything in the nature follows some basic rules and regulations. That means the length, mass, time, or maybe the velocity, acceleration, likewise different things present in the nature, they changes their amount, they changes their quantity in different styles. I repeat, different rules and regulations. And there we go, guys. Those quantities present in the nature, we call it as a physical quantities. Okay, so let's talk about that. Physical quantities. Okay, so this physical quantities, whatever present in the nature, just like the chess coins, these will change their amounts, nothing but the quantities. Okay, whatever the value of them is there, they will be changing by following some rules and regulations. Okay, that's my point, guys. All right, now these physical quantities will be changing. Okay, and whenever coming to the description of these physical quantities, different physical quantity, actually we have millions of physical quantities in the nature. All right, now these physical quantities, how they change, or what are the rules and regulations they follow. Okay, based on them, these physical quantities were altogether classified into three types. Three types they are classified. Okay, based on the information required to completely describe them. So to completely describe this physical quantity, whatever the things are required, based on them, these physical quantities were classified into all in all three varieties. Okay, the first variety we see. So if at all I took an example of a physical quantity, let's say suppose time. For understanding, we're taking the example. I took an example of a time physical quantity. Okay, or maybe a length. Now whenever I want to discuss a time means, I'll say what is a time. Okay, let's say now let's say it's 11:45. Okay, and just I'm telling a number, right? Whenever I'm describing the time, I'm telling that number 11:45. Okay, 11:45 a.m. Did I say anything like 11:45 a.m. in north direction or east or west direction? No. That means in order to describe a physical quantity completely, if only a number, nothing but a magnitude is required. Okay, those are one set of physical quantities. So in order to completely describe the physical quantity, only magnitude is required, nothing but a number required to completely describe it. That is one set of physical quantities. I repeat, in order to describe those physical quantities, just I need a magnitude, nothing else. Okay, and the second set is those physical quantities, in order to describe them completely, along with magnitude, I want to describe something else. All right, complete description of the physical quantity. Let's understand that again by an example. Suppose, yeah, you are already aware regarding some physical quantities like force, acceleration, velocity, or displacement. Okay, let's take those simple examples. So if I consider the displacement, let's say uh, whenever I'm describing a displacement, I'm supposed to say that the candidate moved from one point to other point, traveling some distance. Okay, traveling a magnitude, let's say 5 meter in north direction. So basically we consider a physical quantity in which the separation between initial final distance along with the direction of the movement both are included. Likewise, velocity also. I need to say, whenever I'm talking about the velocity means, I need to say what is the rate of distance displacement covered. That means how much amount and in what direction. Likewise, force also. So whenever you're applying some force, let's say 10 Newton force I apply. So 10 Newton force means I'm discussing only the number, right? 10. Did I discuss anything regarding the direction? No. That means in order to completely describe it, along with the number, you need to comment on the direction also. I need to say 10 Newton force may be in this direction or 10 Newton force in this direction. So whatever, whenever you're discussing the force, you need to, in order to completely describe that, along with a number, you need to discuss what is the direction also. Okay. So those are the second category, second variety of your physical quantities. Those quantities along with magnitude, in order to describe them completely, both magnitude and also direction is required to completely describe them. Okay. So that's a second variety of your physical quantities. And not only this guys, one more additional stuff here. Along with this magnitude and direction, another rules are also followed by these quantities. Okay, some special rules, like whenever you're discussing about the scalar, actually this first type of quantities, whenever two or more quantities were added, okay, just we added no, just we add the numbers only. Okay, suppose some 2 apples and 3 apples are added collectively. What is that final value means? 5 apples we say. Likewise, let's say a length of 2 meter and length of 3 meter were added. What is overall length means? 5 meter I say. Okay, that means simple addition rules we follow here. Okay, whatever we are regarding till our schooling. So simple addition rules here. Simple addition, subtraction, multiplication, division rules. Simple mathematical rules are called as. Rules are followed here. For addition, subtraction, multiplication, division, whatever. And coming to this, here not the simple maths we can use. A different mathematics we'll use here, which we discuss in this chapter only. Okay. Some special rules are followed whenever you are adding two quantities of this category. Whenever you add two quantities or subtract two quantities or multiplication, when you multiply two quantities, some different set of rules are there. So a different style or a new set of mathematical rules.
Sir, your video is not coming.
Okay, a small glitch with the network guys, just the Wi-Fi was off, just I'm running with this mobile data. The video is stuck in between, not an issue. So basically coming to the second category, a new set of mathematical rules are followed. Okay, whenever you're adding, subtracting or multiplying. Okay, so that's the second category of the physical quantities. Okay, and coming to the third category of physical quantities, in order to describe them, basically completely describe them, we require a magnitude, a number, and along with that a direction. Okay, in what direction, and at last along with that magnitude and direction, one more additional thing is required. Okay, which is not given in many of the books guys, just I'm letting you guys know that. So along with magnitude and direction, the area, which we talk about that later, that's what we call as area vector. Okay, so in order to completely describe a physical quantity, you will require magnitude, direction,
Sir, your video is not audible, sir.
Magnitude, direction and area is required. Let me know, am I audible to you? Am I audible? Am I audible, guys?
Video is not visible. Hello.
Yeah, let me check it out now. So here, magnitude, direction, yeah, check it out, the video.
Yes, sir. Now it's coming.
So coming to this, a third category of the physical quantities. In order to completely describe them, we require magnitude, direction, and along with that, one more quantity, the area. And to say it more precisely, it's not only the area; it is the area vector. What exactly the area vector, that you will get to know in second year. All right. So that's how the three classifications are. To completely describe a physical quantity, the information required is only a magnitude, a number. That's first classification, and simple mathematical rules are valid for that. And that is your first category of physical quantities. And we name that physical quantities as scalars. And coming to the second classification, second category of physical quantities are, in order to completely describe those physical quantity, we require a magnitude. That's not enough to completely describe it. Along with the direction is also required. And it follows some special rules of mathematical, unlike that simple addition, subtraction, multiplication, division. So it follows some special rules whenever you want to add or subtract these type of physical quantities. Special rules are valid, and those rules we call it as vector rules. We name those rules as vector rules. Okay, and we name those that corresponding physical quantities as vectors. And coming to the third classification, these are this physical quantities. In order to describe them completely, a magnitude is required, a number, and direction, in what direction that quantity is, and along with that one more thing is required, that's area or area vector we call it as. Okay, and coming to the mathematical operation of this doesn't follow vector rules of addition or subtraction. No, it doesn't follow this vector mathematical rules, but in spite it follows the scalar mathematical rules. Okay, so it follows scalar mathematical rules. Or let me tell it in another way. That's a universal statement. It doesn't follow vector rules. Okay, in many of the books what they give simply is only magnitude required scalar, magnitude direction required vectors. Coming to the third classification, they won't say anything because basically this is not in your syllabus. Okay, but only in 2 chapters they talk about this, so that's why I'm giving this information also. Okay, and coming to the description of them, this and this, showing the difference between them. Just they say both magnitude direction required for vectors. Here also they won't mention regarding area. They will say magnitude direction are required, but doesn't follow the vector rules of addition. So basically, whenever you're talking about the difference between the vectors and this third category, third variety, magnitude direction required follows vector rules. Magnitude direction required doesn't follow vector rules. That's what they mention in many of the books. Okay. And coming to this one, there's a third classification. We named it as tensors. So altogether 3 classification of this physical quantities are available. Okay. Scalars, and you can comment on some examples on this of the scalars. We have many examples like length, mass, time, and so on. Let me write the examples here. Length, I don't say 2 meter in north. Whenever you're measuring the length of the pen, let's say what the length of this pen means, I will say, let's say it is 8 centimeter in east direction, west direction. I won't mention that. That means length is a scalar, mass 100-gram pen in east or west direction. I'm not mentioning. That means 100 gram. That's complete information. So only a number is required. So mass is a scalar. Okay. Likewise, time and many more examples we have. Okay. So these are all the examples of the scalars. Coming to the examples of vectors, just I give this examples directly. Let's not derive what is a vector and how to conclude whether the given quantity is a scalar or vector. We're not working on that here. Just I'm giving the ready examples for the vectors. Already you might be heard regarding these examples. Displacement, velocity, acceleration, okay, momentum, linear momentum, angular momentum, torque, many more. Have a lot. And in your entire physics, mainly we run behind these vectors. Yeah, we come across scalars also, but many vectors that we discuss. So that's why we need to know like what is a vector and what are its rules and everything, which we discuss in this chapter. Okay, our main focus is only this segment in this chapter. Okay, finally coming to this tensor examples. In elasticity chapter, we come across the terms like stress, strain,
Check your video. Sorry, your video is not clear.
let me know, is the video clear now? Okay, coming back to this, so in your elasticity chapter, you come across the terms like the stress, strain. Okay, that's an elastic property, by the way. Okay, so which are tensor quantities. And not only this, whenever you come to your +2, I mean in your second year, in current electricity chapter or magnetic field and electrostatics, there you see some flux quantities we call as a flux, electric flux and magnetic flux. By the way, all flux quantities are tensors, because in order to completely describe them, you need to comment on the magnitude, direction, and some area should be also required. Okay, so three are required for this, and we call it as a tensors. Okay, so basically we don't discuss much regarding the tensors and its properties. Okay, detailed discussion of tensors will be done in your BTech. Okay, so here in our course we discuss only regarding the vectors, and basically scalars I won't comment on that, because so far till date already you are aware regarding the scalar quantities. Okay, knowingly or unknowingly, you totally work with the scalars only. 2 plus 3 is equal to 5, a scalar quantity. Okay, the mathematical operations, whatever you are doing there, addition, subtraction, multiplication, division, that is completely regarding scalars. So no need to comment on that. So directly we jump over the vectors now. Alright, so make a snapshot of it. Now we discuss what is a vector and what is a within these vectors, how the further classification of the vectors is done and on what basis. Okay, next we see that what are the types of vectors. Take a snapshot, guys, meanwhile. Okay, now so simple guys, to describe completely only a number magnitude is required. It's a scalar. Magnitude and direction both are required, and it follows some special rules which we call as a vector rules. Then those quantities we called as a vectors. And the third classification is a quantity which require to completely describe it a magnitude, direction, and also area. And this doesn't follow the special rules of the vectors, but it follows the general rule, normal rule of the scalar mathematical operations. Then that's a tensor quantity. Alright. Now we see how to represent a vector, then after the types of the vectors. Okay. So whenever I talk about any physical quantity, any physical quantity, and I repeat, we are discussing the vectors. So any vector physical quantity. So I do consider any vector physical quantity. Okay, maybe a displacement, velocity, acceleration, or anything. Okay. Now for that vector physical quantity, what I will do? Let's consider the force. Let's consider one of this example of the vector physical quantity, force. Okay. Now let's say some physical quantity of 10 Newton force is applied in this direction. Okay, I repeat, 10 Newton force is applied in this direction. In this direction. Okay. So here in this process, in order to show that physical quantity on a paper, on board, or wherever it is, okay, generally on a graph paper, in order to show that, what I say, the line on which the physical quantity is there, just I am represented with the dot. This is a line on which the physical quantity is there. Okay, and the physical quantity is what? Force. And how much force is there? 10 Newton. Okay, 10 units, I mean to say that. Okay, so in order to describe that physical quantity, simply what I do, I take 2 points such that the separation between them, okay, that is proportional to the magnitude of that force. That means that separation should be proportional to the how much force is there, what are the units of that physical quantity. Okay, and in what direction, by the way, from here to here, right? Okay, let's say I'll call this point as A, this point as B. What I can comment on the direction of the force from A to B. Alright, and that initial point is A, final point is B. That's how I represent. So symbolically, I mean graphically, how we represent a vector is initial point, which we call as tail, okay, and that final point, just to indicate the direction, this we call it as head, and the direction of this physical quantity is from tail to head. That's the direction of the vector. Alright, so I repeat, in order to describe the direction of this physical quantity, one point to other point, and that is from tail to head, that indicate the direction of the vector, and how much magnitude means. Okay, so here whatever the length is there, or the separation between A and B, we call it as length of vector. Okay, and by the way, this length of vector will be proportional to magnitude of vector. Alright, so basically these are the things which we are defining, okay, for our symbolic representation. I repeat, whenever I want to represent any physical quantity, a vector physical quantity, so what are the rules I follow here? For my convenience, I created my own rules. What it is? I consider one point initial and another point final such that direction of the physical quantity is given from this initial to final or tail to head, and the separation between tail and head, that's a length of the vector we call it as, and that length should be proportional to the magnitude of the vector. Let's understand that in detail. Okay, and that's what we call it as a force vector. Okay, graphically that's how we represent it. Okay, so that's what representation of vector. Of vector. Any vector is represented likewise. Okay, and whatever the dotted line, we call it as a base of vector. It's a base. Okay, just we should be aware regarding all this terminology. The line on which vector lies, we call it as a base of the vector. Initial point or tail, final point or head, length of the vector, and in some cases the length of the vector can be equal to magnitude of the vector, but it not always. I repeat this point, guys, be clear. This length, sometimes it may be equal to magnitude, okay, but not always. Okay. But one thing is for sure, both should be proportional. So what do you mean by that? So suppose, to understand that, let's consider a vector is there of 10 Newton. In this direction, a force vector of 10 Newton is there. Okay. Now what I do here, so I want to represent this vector. So what I can comment here, this should be the direction. That means base of this vector should be this. So let me draw here. So the direction should be in this direction only, right? So just I am drawing the base first, base of the vector, and here actually on this base, up or down, in what direction the force is there? Upside. Okay. So what I can say, tail, head should be somewhere here, tail should be somewhere here. Okay. But if at all I take, let's say, tail I am fixing first. The tail is fixed. Okay. Now with an a proper assumption of a scale. Okay, what is the scale I am taking? Let's consider this as 100 Newton. Okay. So I want to, on a graph paper, I want to represent this 100 Newton. That means I cannot draw 100 meters on a graph paper. Okay, or 100 kilometers on a graph paper I cannot draw. So just to convert this unit into some graphical measurement, what we need to do? We need to assume a convenient scale. Okay, how? I can assume, let's say, 10 units equal to 1 centimeter or 10 units equal to 1 millimeter. According to my convenience, I'll do that. So what I am doing here, I assume 10 units, 10 newtons means 1 centimeter. So with a scale, what is the scale I am taking here? 10 newtons equal to 1 centimeter. With that scale I am drawing. Here how many newtons are there? 100 Newton. That means how many centimeter it should be? 10 centimeter. Let's say this is a 10 centimeter. In this upward direction, there you will get the head. Okay, so that's a head. So basically I cannot see the force, right? Repeat, just I am pushing an object in this angle with 100 Newton force, and as I cannot see that, simply what I am doing, guys, just I am representing every 10 Newton means 1 centimeter. Okay, with that appropriate scaling, I am drawing on a graph paper with this tail, with this head. Separation between them should be how much from here? That is 10 centimeter. Suppose in spite of taking 10 centimeter, 10 Newton equal to 1 centimeter, if I take 10 Newton equal to 1 millimeter, this will be 1 centimeter. Okay, 100 Newton force graphically represented comes out to be 1 centimeter. So that's why I'm telling length of the vector is proportional to the magnitude of the vector. That's my point. Okay, and the vector falls on the base of the vector with from the and the direction is from tail to the head. So that's what the basic representation of a vector. Okay, and from now, whenever I want to discuss any physical quantity, okay, maybe a displacement, velocity, acceleration, force, momentum, torque, or whatever it is. These are all the physical quantities which I won't be able to see directly from my eyes, right? With my direct eyes, I cannot see that. Just I can feel it. Okay. So just I'm trying to convert my feeling or the sensation of a physical quantity to what? On a graph paper. Okay. Just I can feel that I'm pushing some object with a 100 Newton force in this direction. So that feeling, what I'm doing, in whatever the direction is there, I'm drawing a base. Then after, with a proper scale on that base with initial and final points, I'm plotting with appropriate as assumed scaling, a convenient scale. Alright. So that's what we do is, every feeling of a physical quantity, just I plot it on a graph paper. Yeah. We consider the example of force. Next, we do consider the displacements, velocities, accelerations, and many more. Okay. Alright. And the last thing is here, this is initial point or the tail A, this is a final point or the head B. Okay. And symbolically, this vector can be represented as the initial to final, right? The first tail letter should be here. You are representing tail with letter A, head with letter B, A and B. Okay. Maybe with bold letters I can represent this. Okay. Or sometimes I represent with a line over that tail, actually first tail then head. Okay. First the letter constituting the tail and the letter constituting the head, and a line over that. Or sometimes we write it as AB. By the way, it's a vector, right, from tail to head. So symbolically it is represented like this, which says that tail is A, head is B. Okay. Or in some other cases, I'll say, just directly I'll say, it is a vector AB, right? Vector AB, or simply I write it as A bar, or some B bar, some small letter. Okay. With a small letter, A bar or B bar, I represent this. So this is a basic or the general representation or notation of, symbolic notation of a vector. Alright. So how to convert a feeling to a graphical vector we saw. And the second thing is what? After drawing that graphical vector, how to represent using some letters. That's a notation. Okay. Both we discussed, guys. Okay. And next we need to discuss what are the types of vectors. Okay. We put that in our next class. Alright.